Well, good afternoon, everyone, and welcome to this SCI webinar on the chemistry of CO2 and its role in decarbonisation. My name is Mark Harrison, and as chair of the SCI Energy Group, and on behalf of the Society of Chemical Industry, I'd like to thank you for taking the time to join this webinar, which is the second in a series of three. For those of you who aren't already aware of the SCI, I'd encourage you to visit our website, and the details are shown there on the screen. SCI is a charitable organisation founded in London in 1881, and it operates at the interface between industry and academia to foster innovation, members networking and development, and to contribute to the public understanding of science. I think of particular relevance for the presentations today and for this webinar series as a whole. I'd like to make you aware that the SCI publishes 3 significant journals in the subject area. That's Greenhouse Gases, Science and Technology, Energy Science and Engineering, and Biofuels, Bioproducts and Biorefining. I hope you find today's webinar valuable, and now I'll hand over to my Energy Group colleague, Dr. Mariam Bayati, who will chair today's proceedings.
Good afternoon, everyone. My name is Mariam Bayati, and I'm a member of SCI Energy Group. As Mark mentioned, I will be chairing today's event. So I would like to welcome you all to this webinar concerning the chemistry of carbon dioxide and its role in decarbonisation. So today we have a fantastic role of the speakers. This includes Professor Mercedes Morato-Waller from Heriot-Watt University, Dr. Rico Kanefka from Suez Company in Germany, Dr. Nim Rahimi from Massachusetts Institute of Technology, USA, and Dr. Andy Walker from Johnson Matthey, UK. So this is the second of 3 webinars in this series, and the subsequent another event has been scheduled for the Thursday, 5th of November. I would like also to introduce my group colleague, Mark and Jared, who will be helping to coordinate the Q&A session following the presentations. Before I introduce our first speaker, I would like to remind you about some bolts and nuts of this webinar. I'm pleased to say that there have been lots of interest on this webinar series, with over 57 people has registered just for this particular webinar. So I'm sure you will understand why everybody has been kept mute but the speakers. But you can ask your question and post it at any time during the presentation using the function provided on the webinar page. When you do, please remember to include your name and your organization or the company name as well. Mark and Gareth will be reviewing these questions and developing a representative set of the main Q&A panel, which is scheduled for the final parts of this webinar, once all the speakers have presented. If there is any question of clarification for individual speaker, we may take these at the end of their presentation too. It's now my pleasure to introduce our first speaker, Professor Mercedes Morato-Waller from Heriot-Watt University. Is leading the development of UK Industrial Decarbonisation Research and Innovation Centre, in brief IDRIC. She's also Associate Principal and Director of the Research Centre for Carbon Solution, RCCS, at Heriot-Watt University. Her internationally recognized track record covers the energy system, carbon capture utilization system, integration of hydrogen technology, and low carbon fuel. If I could now hand over to you, please, Mercedes.
So good afternoon, as I said, and first of all, thanks very much for the opportunity to present today and give you a little bit of a catch-up of what we have been doing on the last months. going back to May when I did the presentation to the SCI Energy Group as well. So again, thanks very much for welcoming me again today. So I think that the first message I want to give today is really in the context of everything that is happening around us with a pandemic, as we see now many countries getting into a second national lockdown. And the message still to take is that it's not too late to change course when it comes to climate change. If you have an opportunity to look at the World Economic Outlook report published by the IMF just a couple of weeks ago, really, it was very clear that in the midst of all this all this COVID crisis that we are living, we still need to make sure that we mobilize to prevent a climate crisis. And there were some key messages here as well, going around the policy tools that we need for this to happen, and also making sure that a green investment is included in the budgets as we're actually coming or trying to come out of the COVID-19 pandemic. So I encourage you to have a look at the report, because it does set the tone in terms of the coming months and the coming years, and how we need to make sure that we do not forget the biggest threat that we have, really, or one of the biggest threats to economic growth globally, and that is climate change. So moving to the next slide, we need to decarbonize, as you all know. We need to do this at a global scale. And I think another key message for me is that this is feasible, but it has to happen at a global scale. Now, the maths and the numbers are daunting. I'm not gonna negate that. And if you look in terms of one of the McKinsey reports, we are looking at over 550 gigatons of CO2. And putting that into context, that will only give us a 66% chance of a stay within the 1.5 degrees C. So we need to be aware of the magnitude of the scale of this challenge, but also I think we need to keep in mind the benefits of what we are trying to achieve here. And this is really the benefits of moving to a low carbon economy. And the slide that you have in front of you on the left-hand side gives you some of the numbers and the indications of what this means on a global scale, looking at those trillions of dollars, US dollars. And then if you bring that to the case of the UK, and that's the right-hand side of your screen, what we are looking here is that the growth, estimated growth of this low carbon economy, it could be 11% per year. And this actually is 4 times faster than the rest of the economy. Of course, these numbers were published before we went into the pandemic that we are living, so they will need to be adjusted. But regardless of that, please do keep in mind the benefits of moving into this low carbon economy, and that actually they are significant in the context of the UK as well as globally. So what does this mean from the point of view of the UK setting up this net zero target? Well, if I have to summarize it on just a few words, really what the net zero target means is that there is no place to hide. That's basically what it means. Now, there have been in the past messages as well about the difficulty in terms of reducing CO2 emissions is because they have to be decoupled from economic growth. And if you look at those graphs that you have there, the top graph in there illustrates and shows very clearly that in the case of the UK, we have been able to decrease our CO2 emissions significantly. These are territorial emissions, but at the same time, we have been able to grow our GDP. So it is possible. Now, the graph underneath, also taken from the Committee on Climate Change report, paints a very interesting picture here. And this is actually what I will be focusing on the rest of my presentation. We have been doing relatively well. In fact, we've been going in some cases above the target that we have set ourselves to reduce CO2 emissions. But we need to be very mindful here that the reason why we have achieved this is because we have decarbonized the relatively easy sectors. And I'm saying relatively because it's really nothing easy in decarbonization. But we have decarbonized to a really large extent our power sector, our power generation. And that is why that overall number of our CO2 emissions is coming down. What we have ahead of us is actually those sectors that are really difficult to decarbonize. And what I like to say is that really we don't have any more low-hanging fruit. So for us to meet our carbon targets, our net zero targets, we're going to have to do a lot of difficult things, and we're going to have to do this together, and we have to do all of it. There is no place to hide. If I focus in industry, and that's what I will be talking about the rest of my presentation, the industrial sector has also been doing relatively well in terms of decreasing the CO2 emissions and increasing output. It has been in some cases because we have improved energy intensity of some of our sectors, and in some cases as well, I have to say, is because some of our industrial sectors are less carbon intensive. One of the things we have seen is a decrease of refinery production, and that's quite energy intensive. So that's really the picture. Going forward, we're going to have to do a lot of different things, and not the easy ones, as I said. So what mechanisms we have in place, and I just want to add here that these mechanisms are not going to achieve everything that we need to do to decarbonize. These are very important steps, very critical steps right now, but we're going to need a lot more of efforts jointly to be able to decarbonize the UK. The picture that you have in there actually gives you some of the major UK funding mechanisms now that we have, and I will be focusing on the one that you have on your left-hand side, that one there, on Industrial Decarbonisation Challenge. But before I do that, as you can see, there is a really complex and full picture that is needed. So there is mechanisms like the Transforming the Foundation Industries Fund, and that's the one just to the right of that square, that red square that came up, and that's about energy, resource efficiency, and looking at what we call the 6 energy intensive industries. So the cement, steel, glass, paper, chemicals, and ceramics. These sectors in the UK, we shouldn't underestimate, they actually can produce 52 billion of our UK economy, but they have to be decarbonized. Moving to the right, we have the Industrial Energy Transformation Fund. This program is currently open for the Transforming Foundation Industries Fund. Part of that is already underway. Some of the phases have been progressed. The IETF that you have in the middle there is about industrial switching, fuel switching, CCUS, resource and energy efficiency, and there is a first tranche of funding of at least 30 million. It may be increased, but as you can see on the blue box there is a much larger pot of money that will be released. And then there are other sources of funding, the Clean Steel Fund, and you also know in the case of the UK, there have been announcements earlier on this year about major programs for CCUS and hydrogen. So keeping focus within industry, and that's my focus today, we have the IDC, the Industrial Decarbonisation Challenge, and the program, as you see there, is a total of around 170 million upfront public support, and this will be matched with over 250 million match support from industry and other sources. So what is the IDC, the Industrial Decarbonisation Mission? It's also what we call the Industrial Clusters Mission. And the focus, if you have a look at the map on the right-hand side, is on the 6 clusters there. These are the 6 largest industrial clusters in the UK. And as you see, they cover all the way going from Scotland all the way to Southampton. And also in between, we have areas in Wales, as well as north of England, east of England. And all those together, collectively, they produce around 40 million tons of CO2 per year. To put this in context, what does 40 mean in terms of the UK? Roughly is we are looking around 8%, 7 to 8, below 10% of the emissions in the UK. So by taking care of the emissions from these clusters, we can actually go a long way. And remember, these are difficult to decarbonize sectors to reach our net zero target. Now, why this approach? Well, the approach here is because we want to take a benefit of economies of scale. We want to take advantage as well of shared infrastructure that is already happening or could happen within these clusters. And that will be both at the supply chain as well as the existing workforce. Ultimately, what we want, and that's the red color message at the bottom of the slide, is to create opportunities to work together, and I will mention this several times, so we can actually find these cost-effective solutions to decarbonize. The industrial cluster mission, I should say as well, the banner that you have on blue with the white letters there, is we want to establish at least one low-carbon industrial cluster by 2030, and the world's first net zero industrial cluster by 2040. Again, this will not be everything that we need to do to decarbonize, but it's a significant step taking us into that direction. So I already mentioned the size of the program. I think maybe the other point to mention here is that the program, the overall IDC or industrial clusters mission, is divided into 3 activities, so 3 strands. There is a strand where we're focusing on industrial demonstrators and sharing infrastructure, and this program is 132 million and is administered by Innovate. A second key element of this mission is the cluster decarbonization roadmaps, or cluster plans as they are known now. Is an 8 million program, and this is administered by Innovate. And the third element that you have there, and that's what I'm going to be focusing on, is the Industrial Decarbonization Research and Innovation Center. And that's a 20 million program and is administered through the Engineering and Physical Science Research Council, EPSRC. Maybe a message that I want to give here as well is that the program has 3 elements, but those 3 elements work very closely together, and that's the intention in going forward. And actually, we do need those 3 together working, because that will be the way to really deliver the objectives of the mission. I'm not going to go, excuse me, into details on the right-hand side, but it gives you an idea in terms of we are looking at 1.5 million jobs. We are looking in the order of 320 billion in terms of export potential as well, just by looking at these industrial clusters. Okay, so focusing now into the Industrial Decarbonization Research and Innovation Center. So we have been developing the plans of how this center is going to be operating, what are going to be the main functions, the stakeholders, and putting together really a research and innovation program that will help to achieve the mission. So there are 4 key functions that we have. As you would expect, it's going to be a research where we actually are bringing the best leaders in the field to work together and to actually help in terms of addressing these industry-led challenges. A key element and a key function, of course, is going to be the innovation, and just making sure that we actually try to integrate that research and innovation landscape that sometimes is fragmented and things do not happen at the speed and the pace that we need to decarbonize. And 2 other key elements that we have here is an element of knowledge exchange and an element and a function of leadership. Why do we need this? Because as I said before, there is no way to hide. We need to decarbonize everything. And for that to happen, it will not be enough just with decarbonizing these 6 clusters. I will be very pleased if we do that. But in addition to that, we need to make sure that messages and knowledge is actually shared in between and across and outside the clusters. And the leadership, because quite importantly, of course, it's not going to be just about technology, policy, business models, regulatory framework, but we also need to make sure that we have the right skills to actually be able to deploy these carbon solutions. So all those elements are part of the Industrial Decarbonization Research and Innovation Center. And as you can see in terms of the impact, we have a set of KPIs looking in terms of green economic recovery, boosting the competitiveness of the regions that we are working with, protecting and creating new jobs. Green collar jobs are going to be really critical going forward. And ultimately what we want is that these regions, not only they stay and they flourish, but also they attract inward investment. So I've been talking about IDRIC and stakeholders in the community. So we actually have 142 partners, 142 different entities. And these 142 organizations have come out with a 10 million match support to the funding of 20 million so that we are requesting from UKRI. If you want to see in terms of who they are, as you can see, it's a really good spread. We have 23 research organizations, 74 industrial partners, 35 associations, NGOs, trade organizations, and also working alongside very closely with policymakers and different government bodies and departments. A little bit more now in terms of the challenges that we will be addressing. I think that the first is a key message here that when you look in terms of the emissions globally, they represent around 28% CO2 emissions for energy intensive industries. In the case of the UK, is more around 21%. Those numbers, of course, may have fluctuated over the last months. But what you want to see, or I want you to see here, is that there are significant regional differences. And you can see in the case of Asia, particularly you look into China, not surprisingly, is energy intensive industries are much more dominated by non-metallic minerals. So here we're meaning cement, ceramics, and iron and steel. If you look at Europe, what we have is actually more an even distribution between non-metallic, iron and steel, and chemicals. With all these different sectors, though, there is a series of challenges, and those are very briefly summarized in those 6 boxes. Emissions of CO2, they come from the process feedstock. And this is actually quite important because what this means is the type of technology that may or may not be suited for this particular industry. And if you look at that, those are actually going to be the really hard emissions to decarbonize, because in essence, they're going to require to a big extent that we change the feedstock or we use more renewable or biomass-based feedstocks. These processes are already highly integrated. What that means is that already running at a very efficient and therefore flexibility may not be there. So we need to keep that in mind as we are looking to integrate certain technologies into these processes. Most of them, they have high temperature demand. Most of them also, they have existing plant lifetimes, so they are long, that they are already in place, and we will have to work with them. This is not about building new plants. There is significant infrastructure investment, and we need to make sure that we transition it into a net zero. Also, what is key to keep in mind is that we have what we are producing here, generally speaking, are low-cost commodity products. And the last box, and I'm going to take these 2 together, is that we are operating in global competitive markets. What this means is that the solutions that we put forward, they will have to keep within what the value of these products are. And quite importantly as well, we don't want to do this only within the UK, to the detriment of our UK manufacturing industry and PLC, and therefore end up with having carbon leakage from other regions where potentially actually there may be even less stringent environmental regulations. So these are the challenges that we will be addressing as part of the Industrial Decarbonisation Research and Innovation Centre, IDRIC. In terms of the options, I'm not going to go into detail. The options that we have from a technology perspective, they are around switching to different type of fuels. You can be thinking in terms of hydrogen, in terms of improving efficiency, in terms of how we can electrify heat, energy vectors, CCS, and also other inventions that will be coming along the way. And the different colors used in that graph indicate whether the technologies are already applied at large scale. Those are the green ticks. And they are at a sort of a pilot. Those are orange color, and the gray ones are more at the research phase. Now, important to keep alongside that is that we are going to have different routes. We need to look at this from a holistic point of view. So it's not just only a low carbon technology, but also things that we can do from the demand side or from the energy efficient, and try to make sure that we look at this from a really complete life cycle approach when we look at the chemical sector. And the right-hand side of that slide, the key message from there is, as you can see, there is a time for these technologies. And some of those technologies, excuse me, are already mature and will be looking to deploy them, or strategies to be deployed straight away. Other technologies or other approaches, and they will actually be coming later on. And again, we are going to need to do every single tool that we have in our toolbox to be able to reach net zero target. What IDRIC is aiming here to provide is actually, as you have there, a supporting foundation for technology and policy development. And I want to reinforce this because, yes, it is important that we develop and deploy technology. Without that, we are not going to reach net zero targets. But when we do that, we need to make sure that we also have the policy, we have the business models and the regulatory framework, and of course, the skills related to all of the above. So project examples, just kind of very generally, we are looking at projects that will help us to reduce cost, reduce risk, reduce the timelines, obviously reduce emissions, and as well linked with all of the above economic and policy aspects. The approach that we have taken is we have identified a challenge led from industry. We have facilitated industry alignment for every one of the projects. And this also ultimately will allow us to enable the implementation and the impact of these solutions. So in summary, how IDRIC can help the UK to reach its industrial decarbonisation goals. We will be putting together this research and innovation program. As I said, these industry-led challenges. We are also forming a very active network of stakeholders, as you saw from the number of partners. And really together, we're going to be growing the skills. We're going to be sharing the knowledge and supporting the policy and provide the evidence needed in some cases to actually get these policy and regulatory frameworks in place. I have mentioned this several times, but really collaboration is key. So over the last months, we also have published a series of editorials, opinion pieces in different magazines focused around the chemical sector, focused on cement, on steel. And there is one, if I can just highlight your attention to the one on the left-hand side, Accelerating Decarbonization, sorry. This has just been published actually in the Chemistry and Industry magazine that is part of SCI. And one final message here, I'm sure this is going to be mentioned by the coming speakers as well and in the coming webinars. Collaboration is key. I mentioned that. The role of the industrial chemical sector is key. But also what we need to keep in mind here is that by decarbonizing the chemistry sector, the chemical industries, we are actually helping to decarbonize low carbon manufacturing at large. And if you allow me to throw one of the figures and the numbers, we have looked into several reports. 1 ton of CO2 that is emitted and can be avoided from the chemical sector potentially could actually save 2 tons in terms of the involvement of the chemical sector in the manufacturing of low carbon technologies. That's the IDRIC team. We are currently going through these final stages of the assessment for getting the center in place. And getting the approval and hopefully moving into some of this really exciting research and innovation very soon. Thanks again for inviting me to give you an update.
Thank you very much, Professor Maratovaller, for your very interesting talk on updating us on the current picture of our industrial clusters in terms of their carbon emission and decarbonization plan and the role of IDRIC on the whole part. So thank you very much. And now I would like to introduce our next speaker, which is Dr. Rico Kanevka. Dr. Rico Kanevka is a managing director of Suez Company in Germany. He is director of industrial waste specialist. And today he's going to use a case study to get a pure CO2 to the application of a flameless combustion. So thank you very much, Rico. If I could now hand over to you, please, Rico.
Great. So thank you for the opportunity to be here. Yes, so I'm working for SCI, a French company, one of the global leaders in environmental protection, water, waste, and for sure the technology and recycling. And I want to tell you something a little bit about a case study we started in the region in Germany. It's the Middle Germany chemical region. And we started a study to check how, let me say, waste-based carbon could be used to defossilize the chemical production. Thank you for the opportunity to speak here, and I'm an environmental engineer, so I learned to combine environmental protection and industrial needs, and that's my daily job now at SCI. In SCI, our purpose is, and we think it is, that we are faced with a demographic growth, with climate change, and a lot of social and geographical inequalities. So our job for the future and now is to shaping a sustainable environment now by keeping for sure the possibilities to produce. So we heard a lot in our presentation before that we have not only to save CO2 emissions, to keep our climate targets, or at least try to keep it, and we have to act now, and that's why we want to act now and for tomorrow to preserve the essential elements for our environment. And we're working on all the points. It's water, it could be soil, but now I'm talking today about the air and the carbon sinks. And so SCI is working on innovations for purifying the air, but also working with our industrial clients to defossilize and decarbonize their production. So let me say some small words about my place in the SCI company. I'm the managing director of Industrial Waste Specialties Chemicals in Germany. Industrial Waste Specialties is a European business unit which is mainly dedicated to hazardous waste recovery and industrial solutions. That means we are in the middle of the real chemical production, and our customers discuss about how to drive their business and how to have their business in the future without CO2 emissions and keep the business working. So in Germany, we have 60 employees, more than 100,000 tons of hazardous waste. At the moment, we are working there with a terminal recovery of hazardous waste, an incineration plant in the Middle German chemical region, and also working in the refineries for material and energy recovery. Let me talk a little bit. The case study we started is in the Middle German chemical region. So this is really 100 years and more than 100 years of chemistry. And you see where it is, the triangle, the chemical triangle we are actually talking about and we are working in. You see it here is the eastern part of Germany. You have also a lot of chemical plants for sure in the western part of Germany. But we are situated in this chemical triangle, more than 100 years of chemistry. So, and you see here, let me explain a little bit this picture. Maybe it's hard to read and I go not to all the details in the short term, but you see you have a lot of different sites there working on polymers, on chemicals, refinery products. It's mainly based on, and in the former years, it was based on plastics production, on ground chemicals and acids. And so there is a lot of pipelines, a lot of working together, a lot of working together with intermediate products, which is needed in a different site. And we are located in two of these sites I mentioned here. It's the Schkopau site and the Leuna site with our companies. At the moment, and this is the status now, we are using there our possibilities, our really industrial and technical possibilities for thermal utilization of waste from production residues, solvents, for example, hazardous waste mainly, but also if it fits non-hazardous waste, it depends always on the feedstock we need. And for example, in Leuna, we make a preparation of the energetic use and the material recovery for refinery waste, also for solvents, and also more complicated mixed waste. So this is what we do now and where we located. So we are in the middle of the real chemical production, in the middle of the companies which need carbon, which need ground chemicals, and we have it was too fast, and we have one problem for the future. And if you look more globally to the German economy, or also the economy in this region, Germany, as you all know, for sure, is a very export-orientated company, also country, and it is for sure well known also for the chemical products. And if you look to the actual data, so I go again not in all the details, but there are the numbers from our economy of chemical and pharmaceutical products. And if you look only to the right side here, for the region, the middle region, German chemical region, Saxonia-Anhalt, you see for 2019, for example, we export more than 7 million tons, more than 4 million tons of products, and imported only around 2 million tons. That means, and the same you see on the left side for whole Germany, that means we have a huge gap of products. We export a lot more than we import. It's not only about financials, it's also a discussion. We lose carbon. We lose carbon, and this carbon is only filled by fossil sources. You see here also in these pictures the import of oil or natural gas, which is the main source for the carbon at the moment. And we are losing million tons of resources by doing that, not only talking about financials. And if you look again to the picture I have shown you before, for the relevant carbon substances which is needed now in this whole system of chemical companies, you have ethylene, naphtha, butadiene, methanol, and so on. And the main carbon source and area is Russia. We have from historical times, for sure, also a good pipeline, a so-called Družba pipeline coming from Russia. And every carbon we lose, we fill mainly from this pipeline. So we are in this area mainly focused on chemistry based on fossil sources. And so if you look to SCIS and look to also other companies maybe which are dealing with waste, where we come from a clear waste disposal. We are now and is in a situation that we use the energy of the waste. We do some material recovery depending on the different streams, like paper, like solvents, also more complicated stuff, but it's only for defined streams. And we want to come tomorrow to, let's say, producing ground chemicals from waste. And SCIS 2030, this is our broad program to do that. And so this, our case study is what we can do with our known technology, with our knowledge about really industrial technology, to provide for the future, let's say, ground chemicals we need in this area, maybe not only in this area, but I focus on that. What we know already, how to produce CO2. We produce it during our production of energy out of the waste, and for sure we could do way more. So we want to switch the carbon-based chemical network not to a non-carbon-based chemical network. We want to switch it to a recycling carbon-based network. This is important, and let's say we're talking a lot about chemical recycling. Is it really chemical recycling? Is it chemical production? To be honest, I don't care. Important is we want to supply the future raw materials for the region. And we could use everything we have. I took this picture here from Siemens, for example, because it's a very good one to see. We are not talking only about CO2. CO2 is only one part of this chemistry. We are talking about hydrogen. We are talking about combined products, methanol, which could be maybe produced from CO2 and hydrogen. But maybe you can also have some carbon sources directly from waste. And so for SCIUS, we are technology open and target open. That means we look what our customers need, and then we implement the solutions, and we check what are the new technologies. Universities study new products, maybe new catalysts, whatever we can use to bring back the material out of the waste. And therefore we say, and I say, we use materials formerly known as waste to have the carbon feedstock for the future. So you could also work on very complicated pictures. It's not the time for do that now, and I only don't show you a lot of numbers. But we're working with all the materials and with all the possible. You saw also biomass, for example, in the presentation before, mixed waste, hazardous waste. We have all this feedstock already. For using that for creating energy, fuels, and so on. And now it's time to step forward to use this feedstock in different processes to provide the ground materials for the chemical industry. Let me show you one example in this study. Thanks to ITEA, Dr. Figini, we worked since some years together with the technology they invented, and we checked where we can use it in our processes. One of the partners, I told you we are technology open, but this could be a solution. And I want to introduce this flameless pressurized oxycombustion as the source of waste-based carbon. So CO2 we also have in our normal incineration plant now, but this is more efficient here. And if you look not only on financials, we heard also it's always between material, financials, and CO2 savings. If you look on producing CO2, this is a different approach. Then this could be a good idea. If you look to this process, then you see it's not a classical incineration, it's an oxidation reactor. So incineration is also an oxidation, but here we're working really on only with oxygen instead of air, and we use it with fuel or slurries. The fuel here is waste. I don't go too much into the detail, but the steps is oxidizing, energy recovery, and for sure at the end CO2 recovery. That means this process could provide energy and in the same time CO2 out of a dedicated waste stream. And this is what we check in this area for chemical production. What are the advantages or maybe the disadvantages of oxycombustion? For sure, the oxycombustion, because you don't have the nitrogen in the air, you have the mass and the volume of the flue gases strictly reduced. That means your plants will be much smaller, much efficient to build, because you don't have to use the nitrogen of the air for the incineration, and you don't want to have it. So the flue gas at the end is mainly CO2, which makes it very easy and more efficient to capture. If you don't incinerate nitrogen containing waste, it's also because you have the nitrogen from the air, you have normally no NOx emissions, and you have also less heat loss because your flue gas is smaller, and you can build your plant also smaller and more efficient. On the opposite side, talking about costs, yeah, for sure, you have to get the oxygen, and oxygen is more expensive than air. Everybody knows that. But this is one point we have to face. And for sure, you need this air separation units, and you need the CO2 compression or CCUS systems if you compare to a standard incineration. But we think these are low costs, to be honest, compared to what we get. For example, I'm not talking about all the possibilities, you can read it in a lot of papers, how to come from CO2 to CO to methanol, including hydrogen and so on with electrocatalytic reactions. This is not my point here, but we have these technologies, and I think we're getting nearer to an industrial technology here. But I want to show you how we could and how we want to use this in the future. I start from the incineration. I could also start from the product life cycle. This is if you have a cycle, then you can start wherever you want. So I start because I came from this flameless oxy-combustion. I start with the flameless oxy-combustion, for example, which creates energy and CO2. Then you go to these reactions and all the other possibilities you have to come from CO2 to something you need. And if you remind, in our chemical parks around the middle German chemical region, you need CO2 direct, but you need also methanol and all the other stuff, carbon-based stuff for the chemical production. For sure, you need some more energy than you can create from the waste, but we can use the energy from renewables. So this is not really a CO2 problem for us. So there could be a good combination between the two. Then you have the product life cycle. That means you make your products, and at the end, and this is what we know also already at SCI, we provide the perfect raw material waste mix for this production. And the flameless oxy-combustion cannot incinerate everything. You need the feedstock, and you need the perfect feedstock for that. And this is our core business at SCI since long time, to find the raw materials. I'm talking less and less about waste for this production. That means if you look to this carbon cycle, SCI wants to be the missing link in this chain. Yeah, you have the chemical companies, they produce, also since 100 years and longer, methanol or other waste carbon-based products like plastics. We know also the production of the carbon substances like methanol now. Then you have the product life cycle. We know that we have how to collect the secondary material, and also we know how to provide a new carbon source out of this material. And we also look on what is the best solution there? Is it a small and flexible on-site solution, or is it maybe a large-scale one to prevent too much transport? Just to show, it's not only incineration, oxy-combustion. We are technically open and look to also different possibilities. I want to show you a second example from UK. There is I think since 2013, a plant, Syna and Suez CETA, first secondary fuel plant, which uses plastic, again a carbon source, by different steps and getting not to CO2, it's getting to diesel fuel. But to be honest, whatever you do, it helps you to decarbonize your chemical production. And because looking to my time I have, I think I have to come to an end soon. I want to summarize, sorry for not going more into numbers and details of the processes, If you are interested, please contact us. We are collaboration is key. Yeah, we heard that before. It's the same for us. We are only one part of this chain, but what we see, it's possible, and it will be possible in the near future. We are not talking about centuries. We are talking about years, maybe. But we are not so far away from defossilize the chemical production. And if you look to Germany and to our region, we have to close this carbon cap because we cannot always import the oil. So we're using the waste formerly known as waste, secondary raw material, instead of the fossil sources. We use, besides the standard, we all know, sorting and standard recycling, now the chemical recycling, for example, by producing CO2. Yeah, we know as company since long time the needs of our chemical production, and we want to fit to it. And it's very key to be technology open. There will be not one technology, there will be, in our case, we think a lot of technologies which has to be fit into the chemical production. And we can solve the problem of the different technologies by providing the perfect dedicated feedstock for them. And for example, these technologies like the ITEA isotherm oxycombustion I've shown to you can efficiently provide CO2, which can also at the end used as ground product for the chemical industry from a dedicated feedstock we provide. The new technologies, catalytic reductions, reactions, whatever you have, and you have a lot, and you can read a lot about that. There are a lot of people working on that. And the sector coupling, for example, with power to X, power hydrogen providing, can provide for our region the ground chemicals. It's a huge step because we need a lot of these ground chemicals. So where the waste and all the waste should come from, we have to import also waste. So waste is, if you talk about export and import from waste, you have to clean your mind and say, okay, it's an importation of raw materials like you import oil, and not talking always about, oh, waste imports I don't want because it's waste. No, it's raw material. And this is also very important to know. And if you look to SCIUS 2030, we want to be the missing link in this carbon chain, not only in carbon, but in this carbon chain. So we use the carbon sources from the materials formerly known as waste, not only in the Middle Germany region, but we are very near there now. And it's we do that to prevent CO2 emissions. We think it's the only way to secure this chemical production in this region for the future. Otherwise, we have to stop that. So it would be a huge impact on this region. It's also reducing our dependence from oil, gas, and countries like Russia. It's not only a dependence on the carbon, a dependence on the oil, it's also a dependence on the countries. And we think it is the way to keep our wealth in this region for the future. Maybe it's the only way, because besides the chemical industry, there's not much in this region. So let me thank you for your time, and so I hope I kept my time, yes. And sorry for not having more detail, but you see, we are not so far away from using CO2 as ground material for chemical production. Thanks a lot.
Okay, I would like now to thank Dr. Kanavka on this interesting presentation on chemical recovery, chemical recycling, and recovery of materials and energy, which is a key to our future industries. Now, I would like to introduce our next speaker, Dr. Mim Brahimi from Massachusetts Institute of Technology. Mim is a postdoctoral associate at Department of Chemical Engineering, and he conducts research on developing of various electrochemical processes on carbon capture and utilization. He served as a guest editor of several journals, including a special issue on New Frontier in Carbon Capture and Utilization and Storage for Sustainability Journal, And today he's going to present us about new frontier for electrochemistry in addressing climate change, carbon capture and storage. Now, if I could hand over to you, please, Mim, to continue with your presentation. Thank you.
Thank you so much for the introduction, and it's a great pleasure to be here. Today I'm going to talk about new frontiers for electrochemistry in addressing climate change, and I'm going to specifically focus on carbon capture and storage. So electrochemistry is a powerful tool when it comes to tackling climate change. It can assist in different ways. For example, a very obvious example is electrochemical energy storage, such as batteries, in which we can use, for example, for electrification of transportation through electrical vehicles. Also, we can use it for grid scale storage. The other example of using electrochemistry for tackling climate change is electrochemical CO2 conversion, which we can use chemicals and fuels from renewables as a source of energy and CO2 as the initial material. The way these two technologies are helping climate change is by avoiding further emission of CO2 and by reducing fossil fuel consumption. Rather than fossil fuel, we rely on renewables or these new chemicals or fuels that we're producing through electrochemical CO2 conversion. So another way we can use electrochemistry to tackle climate change is using electrochemical processes for carbon capture and storage, which is considered to be a new frontier of electrochemistry when it comes to climate change. The way this technology is working to help climate change is by avoiding further emission, by capturing CO2, and also it can serve as a negative emission technology. So the main focus of my talk for today is focusing on electrochemical CO2 capture processes. To give you, to refresh your mind about electrochemical processes, so an electrochemical reaction is basically a chemical reaction with electron. So having this electron in this reaction gives us the ability to integrate renewable sources of energy, renewable sources of electricity. So that means we can use this as a driving force to go forward with this reaction or go backward and generate electrical current, like what we have when we discharge our cell phone battery. Electrochemical system has unique advantages. For example, they rely on renewables. They are modular, so it's easy to scale up. And it's easy to retrofit, and it's a plug and play system. So why not using this as a new alternative for carbon capture as an additional asset to those technologies that we already have, like absorption, or membrane-based system? And this can be used to be implemented for carbon capture from different sources, for example, air and other point sources and mobile sources. But the key question here is how to translate these fundamentals of electrochemistry into a system that can selectively capture CO2 from a mixture. So in this talk, I'm gonna review 4 groups of technology, 4 groups of approaches that we can use to translate electrochemical fundamentals into a system that can selectively capture CO2. For the first 3, I'm going to overview the process, and I'm going to spend some time on the 4th one, electrochemically mediated amine regeneration, which is to give you a taste of how we can go from fundamentals all the way to design a system that can be used for industrial flue gas, for example. So for the first one, we have electrochemical generation of nucleophiles. In this case, what we're doing, the core idea is we electrochemically generating a nucleophilic center. For example, in this case, through using a organic molecule like quinone molecule. By reducing this, we're generating this nucleophilic center, which is attractive for CO2 from its electrophilic carbon center. So as a result of this reduction, we have a chemical reaction also with CO2, so we can selectively capture CO2 through this reaction. In order to regenerate this molecule and produce pure stream of CO2, we just need to go backward with this reaction, doing the oxidation of this molecule. So by going back and forth between this reaction, oxidation, reduction, reaction, we can selectively capture CO2 and then remove it as a pure form of gas. Quinone, of course, is not the only example. There are other examples, for example, bipyridine or thiolate, But the key similarity between all of these molecules is by reduction of them, we're producing a nucleophilic center, which can selectively capture CO2. To use this fundamental in a system, for example, here I'm giving you a schematic that shows how a process rely on this mechanism works. In one hand, we have a mixture of CO2, let's say with nitrogen. We have a gas diffusion electrode, and on the cathode, where we do the reduction of this molecule, what happens is we selectively capture CO2. And then later, on the other hand of the cell, we oxidize this molecule in order to release CO2 in the pure form, which we can wash out using a sweep gas. So overall, what we do here, through this mechanism, we generate a nucleophilic site, capture CO2, and reverse the reaction to regenerate CO2. So this is one way we can use electrochemistry for carbon capture. The other way is using electrochemical modulation of proton concentration, or pH swing. A group of electrochemical reactions called proton-coupled redox reaction, in which in addition to electron, we have also proton. That means if we go forward with this reaction, we can consume proton, and if we go backward, we can generate proton. That means we can play with the pH of a solution. And we also know that the CO2 solubility is a pH-dependent process. That means we can absorb CO2 as bicarbonate and carbonate at higher pH and desorb it at low pH. So basically, taking advantage of this pH sensitivity, combining it with this reaction that can play with this pH concentration, we can design a system that can capture CO2 as bicarbonate and carbonate and desorb it as CO2 gas. So this system, the mechanism is relatively simple, but the kinetic might be slow because of the slow kinetic of the absorption itself. People use this type of mechanism to design system. For example, here they used a soluble organic molecule, a proton-coupled redox reaction, in which by reduction of that molecule and also involving protons, they can locally increase the pH. So they absorb CO2 as bicarbonate in this side of the cell. And then later, by doing the reverse reaction, for example, in this case, we have hydroquinone, benzoquinone. By doing the reverse reaction of oxidizing this hydroquinone, the pH of this section of the reactor goes down, and then we can desorb CO2 in the form of gas, and then similar to the previous system, just using a sweep gas to wash it out. So this relies based on an organic molecule, which is soluble, and that molecule is the redox active. We also can use electrode that could host proton. In that case, the electrode itself can intercalate, deintercalate proton in order to modulate this change in pH. For this particular configuration, what I'm showing here, I'm using an absorber. I'm absorbing CO2 as bicarbonate using, let's say, potassium carbonate, sending it to the anode chamber of that electrochemical cell, which is separated by using an anion exchange membrane. Here, I'm increasing the pH. I'm decreasing the pH of that particular chamber by introducing proton ions, playing with the equilibrium of bicarbonate carbon dioxide in order to remove CO2. And then later, on the other hand, what I'm doing is regenerating the pH in order to make it ready for further absorption and sending it to the absorber. So basically, we're taking advantage of CO2 sensitivity towards pH and play with electrochemistry in order to capture and release CO2 selectively. So the third mechanism is relying on a capacitance. So, and it's electrochemical capacitance absorption. Similar to the previous case, in this case, I'm also absorbing CO2 using an absorber and then absorbing as bicarbonate, and then sending it to an electrochemical cell, a capacitance. In this case, what I have here is one chamber electrochemical cell by having two anion and cation exchange membrane. These are ion selective membranes. And what happens here when I charge this electrode is that I'm selectively absorbing this ion on the surface of this electrode. So I'm selectively removing this bicarbonate from the system. And obviously by reversing this, I can again remove this adsorbed ion and just wash it out and generate a pure CO2 stream. So these fundamentals of this capacitance adsorption was used to design also a hybrid system. Again, this is relatively simple mechanism, and also the concern about this system is the capacity is low because it relies on a double layer capacitance, which is normally low. So this fundamental was used to design a hybrid system in which they not only do the adsorption on double layer as bicarbonate, but at the same time in the same cell they also do they also mix it with a metal ion a metal ion, and then do the mineralization at the same time. So basically what happens here is we do that adsorption and then in the same cell do the mineralization. So this process, this hybrid process, is a capture mineralization system, a hybrid system. So that's basically how we do electrochemical capacitance adsorption to selectively remove carbon dioxide from a mixture. So the first method is using electrochemistry for generating amine, or a process called electrochemically mediated amine regeneration. This particular process was heavily inspired by a conventional thermal processes using amine scrubbing. In a thermal conventional process, what we have is in the absorber is selective removal of CO2 using an amine, let's say ethylene diamine in this case, so we generate carbamate. And here, in order to break the bond and desorb CO2, we send it to the high temperature adsorber, apply heat, and break the bond, regenerate the amine as the absorbent, and also remove CO2 in the pure form. So this is how we go from selective capture to removal of CO2 using a conventional thermal processes. So the core idea of EMR, or this electrochemically mediated amine regeneration, is to replace this high temperature desorber by an electrochemical cell. So basically what we have is the same absorption mechanism, the same as the thermal one, selectively removing using an amine. And here, instead of applying heat to break this bond, we electrochemically introduce a metal ion. For example, let's say copper. And this metal ion can bond with this amine stronger than amine with CO2. So as a result, what we have at the end of this oxidation cycle, what we have is this metal amine complex and removal of CO2, desorption of CO2 from this anode chamber, which we can remove it easily. But then we need to regenerate this because we need that pure amine again. So that's what we do on the cathode side. On the cathode side, we electrochemically deposit this metal ion, this metal center on the surface of the electrode. So we end up having that metal surface and regenerating amine to send it to the absorption column for further absorption and repeating the cycle. So this is how it works for the EMR process. So ideally for EMR, we're looking for a continuous system in which we can have absorption and desorption unit combined together, and then we can run for example, flue gas removal for a long-term operation. But before jumping into that relatively complicated configuration, we needed to further study the fundamentals of this system, specifically the electrochemical reaction itself. We needed to answer many questions before designing the actual experimental setup. So here I'm giving you an example of one question to give you an idea of how to design smaller scale experiment to answer this particular question, and then use that answer later from when we design the actual experiment. So here the question is, what is the electron utilization for this particular system? By saying the electron utilization, I mean how much CO2 we can desorb per mole of CO2 we're putting into the system. So that's a key consideration when we want to design a electrochemical system. What is the efficiency of this system? So to refresh your mind about the case of copper as the electrode and ethylene diamine as the amine, here what we have in the anode side, which is the desorption chamber, is by oxidation of 1 mole of copper, we withdraw 2 mole of electron. This mole of copper can react with 2 moles of EDA carbon dioxide, which result in desorption of 2 moles of CO2. So what we have is ideally 2 moles of CO2 for 2 moles of electron. So the electron utilization is 1. 1 mole of CO2 per 1 mole of electron. So we needed to know what is the actual experimental electron utilization for this process using EDA and copper. So we studied this experiment in a particular configuration, just more on the control media, focusing on the electrochemical cell. And what we observed was the upper boundary limit for the electron utilization was 0.8, which is the key parameter, and we have to target that when we operate in a larger scale experimental setup. So this was just an example of how to find answer to some of these fundamental questions, which can be used for later when we design the actual experiment. So those fundamental experiments are mostly around the electrochemical cell itself. But this is just one part of the actual process. What we need to do is to study the actual integrated process from the absorption to desorption and doing this continuously. So to study that blue box, the actual we build the setup, which is sort of a lab scale setup, which consists of column desorption and all the controllers. And this is a relative what is complete depletion. What you do is basically switching the polarity of the electrode. So that's what we included also in this experiment for 2 hours change of polarity. So as you can see here, the system was very reversible for the 2 ranges of temperature we worked on, 50 and also 25. We also, the gas desorption was because of the electrochemical current that we put into the system. Here, for example, you can see there is no gas production. And this is actually when we don't have any electrical current to the system. The gas production is also very close to the theoretical value. This represents that 80% of the efficiency. So that's how we use what we've learned from the smaller scale experiment to when we operate a long-term experiment. So that's that represents that 80%. So by showing this graph, I'm also showing the quality of the gas I'm desorbing, and this shows 100% CO2. So there's no vapor, and there's no, let's say, amine vapor also in the desorbed gas. It's pure CO2. So by showing this example, I hope I was able to show that how to go from a fundamental electrochemical reaction to sort of like a proof of concept scale experiment, and all the way to a more integrated experiment, including absorption and desorption. The same systematic study can be done for other mechanism and other approaches of electrochemistry that I show at the beginning of the presentation. So to sort of wrap up this presentation, I want to go back to those all different mechanisms of using electrochemistry to selectively capture CO2 for a wide range of mixtures, for example, from a flue gas or in general high concentration CO2 streams, and also air. So if we look at the current status of these technologies, we see that most of them are developed at proof of concept or lab scale. So in the future, if we want to make this suitable for like an actual industrial, for example, industrial power plant, what we need to do is going towards pilot scale and beyond. And I think one valuable asset here is to use expertise developed for other CCS technologies, like, for example, absorption-based technologies, to use it here and how to scale up that system. I think that's a great opportunity for collaboration from people in the field of electrochemistry and also other branches of CCS. I'm pretty optimistic about this route of CCS, because if we look at the number of investigation in the last 2 years, we see that most of the investigation were done in the last 2 years and still growing. So, and I think there are exciting years ahead of this technology as an additional asset to other CCS technologies. So in conclusion, I showed you a variety of different approaches that we can use electrochemistry as a powerful tool to selectively capture CO2 from either source points or air. And basically, this can be further optimized and improved at the larger scale, at pilot scale and beyond. And as a future direction, what can be done is connecting this unit, because we're producing pure CO2, connecting this unit to a CO2 conversion unit in order to produce chemicals and fuels and also close this carbon loop. So this is particularly interesting because the nature of the energy required for these two technologies are basically electricity. So we need to provide the same infrastructure for both of this. So I think this could be a very attractive future direction for this type of carbon capture using electrochemical fundamentals. So at the end, I want to thank my supervisor, Professor Hatton, and also my colleagues at the Department of Chemical Engineering at MIT, also the sponsors, Department of Energy, ExxonMobil, and IHI Corporation in Japan. And also, I want to appreciate SCI for giving me the opportunity to present this. If anyone is interested to know more about the details, please feel free to send me an email. I would be happy to discuss this individually. And thank you so much.
Okay, thank you very much, Dr. Rahimi, for your very interesting presentation, and also reviewing this sample system on the role of electrochemistry for carbon capture. So thank you very much. So now we are moving to our next speaker, Dr. Andy Walker from Johnson Matthey. Andy is a technical marketing director in Johnson Matthey. Within his role, he analyzes and assessing the regularity, market, and technology drives for the evolution of automotive powertrain towards electrification, which covers both batteries and fuel cell systems. He also focuses on a clean energy transition and its implication both for transport and beyond, including driving the use of clean hydrogen as a key enabler across different sectors. In 2006, he was awarded the Lloyd's Withrow Distribution Speaker Award by the Society of Automotive Engineering. And today he's going to present us with the role of hydrogen in global decarbonization and its direct and indirect links to carbon dioxide. So if I could now hand over to you, please, Andy.
Thank you very much, Miriam, and good afternoon, everybody. So yeah, I'm going to be talking today about a tangential subject in some ways, but a very related one, looking at how hydrogen is going to play a role in decarbonisation and how that links very strongly, both directly and indirectly, to CO2. And this presentation, I think, builds very nicely on all three of the previous presentations. So first of all, Johnson Matthey, really we have a vision within JM for a world that's cleaner and healthier today and for future generations. And what we do as an organisation is apply our world-class science and technology to solve the key global challenges. And the things that we're very much focused on today, obviously climate change is really the main subject here. But part of the way that we deal with climate change is to drive through the clean energy transition. So we'll be talking about aspects of that. Obviously links into population and longevity, and strong impact on resource challenges, as well as we look at some of the angles of the energy transition and some of the technologies that will be used to achieve it and to enable us to control climate change going forward. One of the things that we see that's been a big driver over the last few years is the changing policy environment. And what we're seeing is an increasing number of countries, regions, states moving to net zero and making, in some cases, legally binding commitments to net zero. 24 countries and regions today have defined dates to become net zero. And essentially 2 or 3 weeks ago, that was 23. And then China obviously made their huge announcement of becoming climate neutral before 2060. 53% of global GDP comes from countries and states with net zero targets on the 2050 timeframe. and a year ago this was just 16%. So what we're seeing is a great acceleration, which is fantastic from the perspective of controlling the climate emergency. And one of the other things that we've seen is that COVID-19 has not slowed this trend. If anything, we've seen moves towards accelerating this trend as governments look to build back better and look as they look at the post-COVID recovery subsidies and finances, looking to focus a large number of those, a large proportion, on greener technologies and more sustainable technologies. So just a quick look at a schematic on what net zero actually means. Net zero doesn't mean that everything goes to zero, greenhouse gas / CO2 emissions. It means that we need to balance anything. So we need to get to zero, as many things as we can get to zero. And then the things that are left, which will be things like agricultural emissions, likely some aviation emissions and things like that, we need to balance them by doing things like carbon removal technologies, planting trees, more peatlands, things like that. So essentially it's about getting that balance right. And to do that by 2050 is going to be a big challenge. Here's an example of the European Union's view on one way to get there. The actual details don't really matter, but essentially you can see, as Mercedes said in the first talk, power is the one that's traditionally been quite a strong focus as we've seen the move to renewable energy, but this obviously needs to accelerate greatly as we move through the 2020s and into the 2030s. Because there's no point, for example, in having a battery electric vehicle whose electrons are being derived from a coal-fired power plant. You really want those to be renewable electrons. And we can also see, it's about getting all the sectors there. So moving away from single sector thinking, from blinkered thinking, towards looking at this as an overall system and a complex system challenge. So all the sectors, transport, power, high temperature industrial processes, some of the things that Mercedes touched about earlier, domestic heating and cooking, we've got to do this with everything. And when we look at the UK context, the UK's previous target for greenhouse gas reduction before we committed to net zero was 80%. And as we made that transition from 80% to 100%, the Committee on Climate Change said that making this move from 80% to net zero changes hydrogen from being an option to an integral part of the strategy. And what we're seeing all over the world now is the recognition that we're not going to be able to get to net zero without significantly increased use of hydrogen. And of course, that needs to be low carbon hydrogen. And when we look at the way that this is going to shake down, in general, if you can electrify things, you would tend to do that. So renewable energy, electrification is the kind of thing that's going to be powering the battery electric vehicles, heating most homes and businesses through electric heat pumps, lighter industrial processes, and already extensive electrification of rail networks across the world. But when we look at some of the things that are more difficult to decarbonize, those harder to abate sectors, this is where hydrogen really comes into its own. So within industry, some of the very highly energy intensive applications, some high temperature processes, you look at steel manufacture and things like that. You look at heavy duty transportation, so long haul trucks, heavy commercial vehicles, putting batteries into those as the primary power source doesn't really make sense. They'd need, in order to get the range that you need for those applications, the batteries would need to be very big, makes them very heavy, also makes them very expensive and a lengthy time to recharge. So hydrogen powered fuel cells will be the dominant technology as we look at heavy duty transportation. As we see, some of the larger and long range light duty passenger transport will also move in that direction. Some rail applications, but as I say, the majority of rail we expect to stay electric. And then we look at perhaps the two most difficult to decarbonize within the transportation sector, aviation and marine. And what we're starting to see now is a great deal of interest in the marine sector towards actually moving from heavy fuel oil to ammonia as the main fuel that will be used there. And of course, to make ammonia, you'd be looking to make that out of low carbon or clean hydrogen. In aviation, again, not suitable for batteries just in terms of size, energy density and things like that. So here what we'll see, and we'll talk about this in a bit more detail in a few moments, We'll see sustainable aviation fuels, so drop-in fuels that mimic kerosene today but are still liquid fuels, will be part of the pathway towards a more sustainable aviation network. Although some of you may well have come across the recent announcement from Airbus, who are looking to put into commercial service hydrogen-powered aircraft. This won't be a fuel cell hydrogen-powered aircraft, it will be a hydrogen-based turbine system to drive future commercial opportunities in aviation. But whichever way we look at it, both sustainable aviation fuels or direct use of hydrogen, hydrogen is going to play a significant role in decarbonising aviation, one of the more difficult sectors to decarbonise. So if we switch now and start looking at CO2 and some of the opportunities for CO2, if we look at annual global CO2 emissions, they're massively higher than current CO2 uses, as you can see from the chart on the right. And the current uses of CO2 directly include things like the manufacture of urea, which goes into fertilizer. It's used for enhanced oil recovery, and also other uses such as making fizzy drinks and carbonating beers and things like that. But what we can see going forward is significant opportunities to convert CO2 into products. So looking at the U part of CCUS in a sense, the utilization part. And when we look at the reasons to do this, I guess one of the main ones is the world is going to continue to need carbon-based products. So you look at chemicals, you look at plastics, you look at fuels, because some of the fuels, as we said, you'll need to be looking more at drop-in fuels, certainly for the foreseeable future, rather than electrifying some of the forms of transport, etc. So there's a good opportunity here to make these renewable using CO2 captured from industrial processes, for example, and then used in the utilization phase. But going forward, far more focused on the use of biomass as and direct air capture as the two sources of CO2. Of course, the other advantages are reducing the CO2 emissions by reusing them, reducing the use of fossil carbon, and then there's also the economics as we look at where the world is going in terms of emission trading schemes, in terms of carbon pricing. You can see on the right hand side here the current carbon price down here and the BEIS assumption, so the Department of Business, Energy and Industrial Strategy in the UK, looking at different scenarios for carbon prices going forward, the cost of CO2 per tonne. And what you can see is 2050, somewhere between 200 and 250 pounds per tonne is estimated. And what we're seeing is a number, for example, of oil and gas majors are also coming to similar conclusions in terms of where this carbon price is going to be going forward, on this kind of timescale. The other beauty of converting CO2 into products is that a lot of the time you're going to be using hydrogen, and you've got the opportunity to use clean hydrogen that can actually help us as we move the electricity generating network towards greater use of renewables. Because one of the things that we do need as we move into a more renewable electricity generation network is to have a massive storage of captured energy, and hydrogen is going to be a great way of doing that. So if we look at the current and potential CO2 uses, and I've taken this from the IEA's Putting CO2 to Use document. With CO2, there's a number of things that you can use it directly without doing any conversions, and those are listed over here. But things like controlling the environments of greenhouses to accelerate the production of the required products. Food and beverages still, heat transfer fluids. But there's also a significant number of opportunities that involve conversion. And fuels, we've talked about, chemicals, we've talked about, Rico mentioned both of these earlier. And CO2 can be obviously converted into fuels and chemicals, but it does require very large amounts of hydrogen. And of course, in order to make this a renewable, net zero compliant route, we need that to be low carbon hydrogen. CO2, also quite a bit of work going on at the moment to use it in building materials and aggregates and cement and things like that, which is an interesting twist on the fact that the concrete industry today is one of the largest emitters of CO2 globally. There's also many options. There's lots of things that you can make from CO2 and several routes as well to fuels and chemicals if we focus on those. So, for example, with sources of CO2, you can use the electrochemical route. So again, building on the presentation that Mim gave, there's a lot of opportunities for electrochemistry going into the future, electrochemical conversions, but also in the purple color, more conventional, so to speak, catalysis to take CO2, for example, using reverse water gas shift to CO to syngas, and to enable us to then use a series of processes and catalysts that are well established today, such as methanol synthesis and Fischer-Tropsch, with Fischer-Tropsch being used to generate hydrocarbon fuels, for example. And if we look at, this is the UK Aviation, their decarbonisation roadmap, what we've seen is many sectors within the UK have built up decarbonisation roadmaps, and really what we're looking to do now is knit them together to make sure that we optimise cross-sector coupling and things like that, so that we're not doing something in one area to decarbonise which is going to negatively impact some of the efforts elsewhere. But what we can see here is current UK aviation CO2 emissions, the projected increase out to 2050, and then the different ways in which they can be the CO2 can be reduced, both in terms of carbon pricing, more expensive tickets, also looking at improved operations and improved efficiency of aircraft, which will go a long way. But it still leaves us, in the best case scenario, round about where we are today. And so to pull this down, a significant contribution is going to come from the use of sustainable aviation fuels. And what's assumed here on the 2050 timeframe by the Sustainable Aviation Authority is about 32% penetration of sustainable aviation fuel in 2050. And this aviation fuel is essentially kerosene made in a sustainable way. Several routes to sustainable aviation fuel use the Fischer-Tropsch catalysis routes, and you can either use, for example, captured CO2, biomass-derived CO2, for example, or you can use syngas from municipal waste gasification and things like that. So quite a few ways for us to enable the substantial decarbonisation of the aviation industry before we end up, for example, with the potential of hydrogen dominating that particular sector. So coming back to hydrogen, we can make hydrogen in a number of ways, but obviously to move towards net zero, this needs to be low or zero carbon. And if we look at hydrogen, when I was a boy, when I was at school, was a colourless gas. Hydrogen is now coloured, ladies and gentlemen, a great announcement coming out today. So we have brown hydrogen, which is defined to be derived from coal, very high greenhouse gas emissions, 19 tonnes of CO2 per tonne of hydrogen generated. Grey hydrogen, which instead of using coal uses natural gas, uses methane steam reforming without carbon capture and storage, and here we end up with about 11 tonnes of CO2 per tonne of hydrogen. And then we've got blue and green hydrogen. Blue hydrogen again uses natural gas as the feedstock, uses advanced gas reforming with CCS, and this can bring the CO2 emissions down to about 0.2 tonnes of CO2 per tonne of hydrogen. So there's still an emission there, and we need to do something with that. But nevertheless, it's a much more effective way of using steam reforming by combining it with CCS, and indeed by optimizing the process. I'll say a couple of words about that in a moment. And then the fourth way is the green, the renewable approach. So here we've got electrolysis, and this has the potential for zero greenhouse gas emissions. But I'll also draw your line to the economics down here, because what we can see is essentially at the moment, the highest carbon forms of hydrogen have got the lowest price, the lowest cost of generation associated with them. And as we go forward, what we will see is as carbon pricing comes in, the grey hydrogen gets significantly penalised because it's a high CO2 emitting technology. Green hydrogen costs will come down significantly as renewable costs come down and as the cost of electrolyzers come down. But where we are at the moment, blue is the cheapest form of low carbon hydrogen anywhere in the world at the moment, in most places in the world at the moment. But what we'll see over time is a development of a mix of blue and green hydrogen based both on cost and on geographical considerations. So for example, if we look at the wind and solar power resources for green hydrogen. Lots of parts of the world are pretty well set up to do a good job at using electrolysis to produce zero carbon hydrogen. But we've got lots of natural gas resources and lots of opportunities for carbon capture and storage in certain parts of the world. So as we move through the transition from where we are today into the complete zero carbon economy in future, we'll see both of these technologies playing a significant role. And I think importantly, finding ways to develop processes which make carbon capture and storage as easy as possible is going to be one of the key things going forward. And just an example here of some work that we've done within JM, by combining a gas heated reformer and an autothermal reformer together, you end up with a system which optimizes the ability to make low carbon hydrogen, but also to have an extremely high carbon capture rate. So with this process, it's been demonstrated that we can get to 98% of the produced CO2 through the steam reforming process can be captured, mainly because it comes out as relatively high purity and in a single stream, which is different from traditional steam methane reformers, where you have two methane streams. One methane stream is used to heat the reformer in the first place, because this is an endothermic process. So as you burn the methane to generate the temperature, to generate the heat, you generate CO2, and then there's the CO2 that's generated at process pressure within the process. So you've got two streams, which makes it more difficult to capture the CO2 and more expensive. With this reaction scheme, it's possible to do that all in one. So I'll wrap up there and essentially, finish with the point that the hydrogen and CO2 value chains are becoming strongly linked, and this will continue to strengthen going forward. Clean hydrogen is essential to enable net zero. Using CO2 to make valuable products is going to make increasing sense, but we need lots of hydrogen for that. This is where the link comes in. The CO2 will transition from looking at capturing from point sources, for example, towards sourcing it directly from biomass or direct air capture. And I think the key thing, for this audience, as we look at the SCI webinar here, clever chemistry and process technology are critical in enabling these moves towards net zero. And if I go back to the start of SCI, SCI was set up in 1881 to further the application of chemistry and related sciences for the public benefit. And I think what we're seeing here, with the kind of applications that chemistry and related topics, related industries, the contribution we can make towards controlling climate change and helping the world through the climate emergency, it's a fantastic opportunity for all of us. So there's some really exciting times ahead. So with that, I'll finish, and thank you very much for your kind attention.
Okay, thank you very much, Dr. Walker, for your very interesting discussion on the role of hydrogen in decarbonization of industries and its link to CO2, and also bringing color to hydrogen today. So now I would like to move to the Q&A panel. So I would like to open the wider Q&A panel of this webinar, and I would like to ask all our speakers to join us. So the first question has been prompted by Raoul Pai, and he's asking, what are your thoughts on an industrial heat pump? What might need to be done to adopt them? And what industries might they be suited, and what politics might be needed? So can I ask one of the speakers to start answering these questions?
I'm not completely sure I understood the question. So looking from an industrial decarbonization perspective, we are dealing with industries that they require a lot of heat, a lot of high temperature heat. And the question becomes then whether one option to decarbonize could be electrification of pumps. So in terms of then when it comes to the option, and I think Andy kind of pointed us into that direction as well, it's going to be a matter of what technologies may be suitable, but also the price of those technologies may fluctuate, for instance, depending on the price of electricity. So what you have to do when you start comparing technological options or option engineering, you need to be aware of what is going to affect prices. And there are some reports published by IEA and McKinsey where it's very clear that the price of the electricity is going to be a key factor in terms of whether we do electrification of pumps or some other option.
I think my understanding was the same as yours, Mercedes. I think what we'll see is a combination based on what's going to make most sense, depending on where you are in the world, depending on the respective prices, but also I think depending on the complexity of the process and the energy intensity of the process that you're trying to do, because in some cases electrification is just going to be impractical for some of the kind of temperatures that we're going to be looking at, and so for there, having that dispatchable source of hydrogen to replace the natural gas that's typically used today, is going to make sense. But I think both, we see both being used, and it really is going to depend on the applications and geographies and commercial considerations as well.
Okay, thank you very much for your insight. So a message from several of these presentations come up, and it's on the critical needs to share and implement decarbonization technology. So this the question is, what option do the panelists foresee for accelerating the wider spread sharing of decarbonization technology, so that that they are not unnecessarily constrained by the intellectual property and financial value protected concerns? And as a follow-on question, what particular technology type might need to be shared most urgently, and how might these sharing be achieved?
I think fantastic questions. I think one of the things that was covered earlier to some extent is, again by Mercedes actually, is we need to start looking at this as a global holistic problem, and indeed as a systems problem across all of the different sectors. I think globally what we'll see and what we've seen historically is certain regions, geographies taking the lead, which, for example, California often takes a mandate-based approach to climate change solutions and things like that, which essentially gives companies confidence to invest in those technologies because they know that they're going to be pulled through within a regulatory framework. We've seen something very similar in China, for example, with new energy vehicles, so battery electric fuel cell vehicles being strongly incentivized. This enables supply chains, global supply chains, to build up and prices to come down. And it's the kind of thing that really has enabled, for example, what we'll see over the course of the next 2 to 3 years is battery electric vehicles becoming the same price as equivalent internal combustion engine powered vehicles. So I think part of this leveling up globally is relating to the building of supply chains, economies of scale, and enabling the green solutions to be the cleanest ones available. I think on the intellectual property side, there will be, obviously a lot of companies see this as companies and countries see this as a great opportunity to bring in revenues both for themselves and as I say for the inhabitants of the countries. But I think what we'll see is the greater good is going to have to be the thing that dominates here, because we're looking at a global challenge. So if anyone else from the panel would like to build on that, I'll take it in another direction.
Yes, Andy, thanks a lot. I think from the view of our recycling and feeding new raw materials, formerly known as waste, kind of view, we have to say at the moment, if I look to Germany and to our region, the only point really is not the technology, it's only financial. It's only the financial point. Everybody knows it's good. Everybody knows we have technologies, we have good technologies, but Andy's have shown it even for hydrogen. The CO2 neutral ones are the more expensive ones. So our chemistry companies in the region, they now asking for, because also of the legal things Andy told us about the price of CO2, they ask now for better and for clean materials, clean carbon sources, and this will push us in the next, not so far away, I think 5 years, to using all the technologies we already have and providing a cheaper, then if you have the carbon price also in your head, a cheaper solution, and then it will work. I'm pretty sure it's not a question of knowledge, it's not a question of technology, it's a little bit a question of organization, of optimization, and for sure we have to keep in mind that CO2 has a price.
One thing I'll say to build on that is that, you know, while innovation is great and innovation is going to be an essential part of pushing things forward, going, you know, into the future, we should start with what we've got now. The whole point of, you know, CO2, it's the area under the curve, it's not what happens in one particular year. So, you know, the key message, if you will, for governments is let's learn by doing, let's get on with this now. Rather than waiting for a silver bullet that's going to come along that may never appear. So I think building on Rico's point, it really is, we've got the technologies today to make massive inroads here. You know, they tend to be more expensive, which is why you need policy to help them to be implemented, but that shouldn't stop us. And at the moment, it's not stopping us doing that.
Yeah,
I think if I can maybe, sorry, Marion, if I add a little bit to that, I think it's a bit in terms of the IP and commercialization. I think we need to be mindful here of the first movers' advantage or disadvantage, depending how you look at that, right? And I think that's a sort of what Andy maybe it was going as well in terms of whether we need to have the right policy and regulatory framework for these first movers to happen. I think in going forward, and one of the things we have been looking as part of setting the development of FITRIC is how we can actually share knowledge rather than data and information, that's where the IP issues become, and how you can actually say about lessons learned without really disclosing what are the intellectual property that you have, and that can be of a huge value as we go through possibly second and third generation of technologies. But there are already, as Sandy said, and Rico, we already have quite a good portfolio of things that we could do now. To some extent, is do we have the right policy, regulatory, the right business models? Because all this is really has to come all together. It's a system approach. And then from there, I think what we can see is we will be moving as there is more innovation and new IP generated.
I think just quickly adds up on that. I think from the academic point of view, there's many also new other technologies that could potentially impact. And I think what I see is sort of a lack of communication between academia and industry, which I think this sort of platform like SCI can just build that connection. I've learned a lot about this industrial scale presentation in this conference. I think this sort of collaboration could also be an additional beneficial asset for the future.
Okay, so moving to the next question, there is a question asked jointly from Rico and also Mim. So it's asked, what issue do the panelists for the impact of the purity of the incoming CO2-rich gas on the separation process can see?
Okay, I'm starting from our industrial point of view. In my presentation, I have shown one technology, the flameless oxycombustion. It has an advantage, and because the gas at the end is very CO2 rich, that means the last step to collect or to clean, depending on what you put in, is less complicated than you take the I don't know, the CO2 from a coal power plant or even from a normal incineration plant. So this is one point, but on the other hand, it's more complicated to operate the flameless oxycombustion, and you need a better managing the input feedstock. So if you combine, and then we are over all the sections, the feedstock, the technology, and at the end the capture and the cleaning, then you have to find the optimum. And this is, I think, a main point. I think maybe you could, from the more scientific point of view, you could say more about that.
I think that's an excellent question. So this is one of our biggest concerns when we try to develop these technologies at higher scale. I give you like two examples. The EMAR technology I talked about based on copper and amine. One of the key problems with having, for example, SOx in the initial gas stream is we might end up with some precipitation. So that's something that we're aware of, which can be eliminated using some engineering solutions. Also, the other example is, for example, we try to use this quinone-based molecules for direct air capture, which when we're dealing with, for example, a significant amount of oxygen, they're sensitive to oxygen. So instead of capturing CO2, they might react with oxygen, which cause some inefficiencies. But we're aware of that, and there are some like fundamental solutions to that. For example, in the case of quinone again, we can tune the structure or just change the structure to make it more selective towards CO2. But that's something that we have to consider, especially for larger scale experiments.
Okay, thank you very much for clarifying on this question and also answering what you can foresee for this particular case. So the next question is, it's asking, given the immediate and urgent near-term need to address the critical challenge of climate change, how should we manage short retention time options such as fuels? Should we value retention time, especially over the next 10, 30 years?
Okay, let me take a go at that. I think the question here is potentially around things like biofuels. So looking at liquid fuels, which in a net zero world, you're still going to be combusting them. They're going to be making CO2, but you absorb some of the CO2 as you make them in the first place. So you've got the kind of cyclic thing there. I think as we look at biofuels and e-fuels, the sensible thing to do is to look at increasing the amounts. And again, this is going to need policy because they're more expensive than regular fuels today. Using policy to increase the amounts that are used over the course of the next 10, 15, 20 years, while we've still got a large number of internal combustion engine powered vehicles on the roads. So, the turnover of the vehicle fleet is anywhere between 10 and 20 years, depending on the type of vehicle, etc. So it does take quite a long time to turn over the fleet. So what we're going to see is net zero regions are going to need to, and are already starting to, ban the sale of new internal combustion engines from 2035 to between 2030 and 2035 in the case of the UK and California. But we're still going to have internal combustion engine powered vehicles right the way through to 2050, even with that framework. So making sure that we can minimize the amount of CO2 that's generated from those vehicles makes sense. And things like biofuels and e-fuels are a sensible way of doing that, in my opinion.
Yeah. Thank you very much. So the next question is, in the absence of a price of CO2, how might we best monetize CCU over the next decade? I mean, what might be a path forward to get CCUS going?
I think, to assume that you are going to be able to reach net zero and deploy any technology of what we heard today, and that's going to come at no cost, and you're not going to need to put any price at all for this to work. I think that's very unlikely, unless I'm missing the obvious here. I think that's going to be unlikely. There need to be really a business models, and there need to be a carbon price. And in fact, when I started my presentation, I was mentioning the IMF report that was published a couple of weeks ago. And one of the policy requirements that they have in there is actually that there should be a floor price for carbon across. And that's quite a big ask, but I think to pretend, there are different models as well and different scenarios that you can actually figure out to actually promote the deployment of these technologies. But we have to realize that this is going to come to a cost. How we can have the best business models, the best policy framework to actually, who's going to pay for this? It's going to be the producers of ethylene, or it's going to be when you actually buy your soda bottle and you pay for that. So I think that's quite an interesting question as well, and obviously we didn't get there today. But for me, the key message is that it's going to come to a cost, and then we just need to make sure that we see what is going to be the best business models for this to happen.
Okay,
I think ultimately, when you look at this, we can't get to net zero without carbon capture, and so it has to be incentivized in the early days. And then building on one of the points that Mercedes made, when you look at the European Union Green Deal, there's going to be carbon border tax adjustments to make sure that the carbon leakage is something that is not going to be allowed to happen, so that you're not penalising the early adopters there. But policy needs to come in to drive that, because, as Mercedes said, economically, this is not the lowest cost approach. But if we're serious about net zero, then we've got to do it, and we've got to invest in it as a global community.
Yes, thanks. I would say the same. We have to pay the price, either now or later.
Okay, yes, that's very much correct. And thank you very much for sharing your insight and also presenting for this webinar. So now I would like to bring this QA session to a close, and thank you all of you for answering the question and also presentation. This was a very interesting webinar, which is covered nearly all aspects of decarbonization from the industrial points of view, the bigger plan and bigger picture on how we can decarbonize the industries, about the role of hydrogen on decarbonization of industries, also on how we can recover chemicals and recycle our waste in a way that we can recover chemicals and also energy at the same time, the role of electrochemistry as one of the major players in carbon capture process. So thank you very much for sharing your knowledge and insight with us. So now I would like to bring this Q&A session to a close. But before bringing today's session to a close, I want to highlight our subsequent webinar session, which this is in a series of concerning the chemistry of carbon dioxide and its role on decarbonization. We are very much welcome you to attend our next webinar session, which is on Thursday, 5th of November. And where you will hear from more academic and industries speakers on this topic. And as you can see that it has been shown on slides. And for the future information concerning these events and event registration, please use the Bit.ly links provided on a screen. And on behalf of everyone, I would like to express sincere thanks to all of today's speaker and their further insight via the Q&A panel. I would also to thank everyone for making today such a great success, and hope to see all of you again at our next events. With that, I would like to draw this webinar session to a close. So thank you very much and have a nice day. Bye.
Thanks, everyone. Bye.